Welcome! In this session, we'll explore LeetCode problem number 1136, Parallel Courses. This problem challenges us to determine the minimum number of semesters required to complete all courses while adhering to prerequisite dependencies. Let's dive into the solution together. The problem we're solving is called parallel courses. Imagine you have a total of n courses, numbered from 1 to n. Along with this, you're given a list of prerequisite relationships, where each pair, A, B, means that course A must be completed before course B can be taken. The challenge is to determine the minimum number of semesters required to finish all courses, assuming you can take any number of courses in a semester as long as their prerequisites are satisfied. However, if it turns out that it's impossible to complete all the courses due to conflicting prerequisites, we should return -1. The input includes the integer n, which represents the number of courses, and the relations array that specifies the prerequisites for some or all of these courses. The output will be an integer that either gives the minimum number of semesters needed or -1 if completing all the courses is not feasible. Let's go through an example to understand this better. Suppose n is 3, meaning there are 3 courses, and the prerequisite relationships are described by the array 1, 3, 2, 3. This means that course 3 has 2 prerequisites, courses 1 and 2. Now, in the first semester, we can take courses 1 and 2 because they don't depend on any other courses. Once those 2 are completed, we can take course 3 in the second semester since its prerequisites, courses 1 and 2, are now satisfied. Therefore, the minimum number of semesters required to complete all 3 courses in this case is 2. Here's another example to illustrate a different scenario. If n is 3 and the prerequisite relationships are given as 1, 2, 2, 3, 3, 1, we see that course 1 depends on course 2 depends on course 3, and course 3 depends on course 1. This forms a cycle, which makes it impossible to complete all the courses because there's no way to satisfy the prerequisites for any of them. As a result, the output in this case is -1, indicating that it's not possible to finish all the courses. Now, consider a case where n is 4, and the prerequisite relationships are 1, 2, 2, 3, 3, 4. Here, the prerequisites form a straight chain. Course 1 must be completed before course 2 before course 3, and course 3 before course 4. In this situation, only one course can be taken per semester because each course depends on the completion of the previous one. So, we'll take course 1 in the first semester, course 2 in the second semester, course 3 in the third semester, and finally course 4 in the fourth semester. This means the minimum number of semesters required is 4. There are several important constraints and edge cases to keep in mind for this problem. First, if there are no prerequisites, meaning the relations array is empty, all courses can be taken in a single semester. Similarly, if there's only one course, it can obviously be completed in one semester as well. On the other hand, if the prerequisites form a cycle, as we saw earlier, it becomes impossible to complete all the courses, and the output must be -1. Finally, we need to ensure that the solution can handle large inputs efficiently, given that n can go up to 500 and the number of prerequisite pairs can be as large as 10,000. These constraints require us to design an algorithm that is both time and space efficient while addressing all possible edge cases. To solve LeetCode problem number 1136, the goal is to determine the minimum number of semesters required to complete all courses while respecting the prerequisite relationships. This problem is essentially a graph problem where the courses are represented as nodes and prerequisites as directed edges. The challenge boils down to finding the longest path in a directed acyclic graph, or DAG, since this longest path will correspond to the minimum number of semesters needed. Now, one approach we could consider is the brute force method. The intuition behind this is to generate all possible orderings of courses and verify which ones satisfy the prerequisites. While conceptually straightforward, the implementation involves backtracking to permute all possible course orders and then validating each order. However, the complexity of generating permutations is factorial, or O(n), which makes this approach computationally infeasible even for relatively small numbers of courses. As a result, this method is quickly discarded as impractical for solving the problem efficiently. A more promising approach involves using topological sorting with BFS, also known as Kahn's algorithm. The key intuition here is to process the courses level by level, where each level corresponds to a semester. Courses without prerequisites can be taken in the current semester, and as these courses are completed, their prerequisites are removed from the graph, making more courses eligible for the next semester. To implement this, we first represent the graph using an adjacency list and compute the indegrees for all nodes. A queue is then used to process nodes with 0 indegrees, which represent courses that can be taken immediately. For each course processed, we decrement the indegrees of its dependent courses, and if a dependent course's indegree reaches 0, it is added to the queue. Finally, we count the number of levels in this process, which corresponds to the number of semesters required. This approach has a time complexity of O, n plus e, where n is the number of courses and e is the number of prerequisites, making it highly efficient even for large inputs. However, it does require careful management to ensure that semesters are tracked correctly. Another effective approach is to use dynamic programming on the DAG to explicitly calculate the longest path from each node. The intuition here is that the longest path from any starting node directly translates into the minimum number of semesters required to complete the courses. To implement this, we first represent the graph as an adjacency list. Then, we use a recursive function with memoization to compute the longest path starting from each node. For any given node, the longest path is calculated as 1 plus the maximum value of the longest paths of its neighbors. The final answer is obtained by returning the maximum value among all nodes. This approach shares the same time complexity as the BFS method, O, n plus e, but it has additional memory overhead due to memoization. While elegant and well-suited for DAGs, it introduces recursion stack overhead, which can be a limitation in competitive programming scenarios. Ultimately, the BFS-based topological sorting method was chosen because it is simpler to implement and aligns naturally with the concept of semesters in this problem. The critical realization that this problem reduces to finding the longest path in a DAG was the turning point in formulating an efficient solution. This insight allowed us to focus on algorithms that leverage the acyclic structure of the graph. Using indegrees to process courses in topological order ensures both correctness and efficiency, and aligns well with the semester-based structure of the problem. When comparing approaches, the brute force method was discarded due to its exponential time complexity, making it infeasible for larger inputs. Between BFS and DP, both have comparable time complexity, but BFS stands out for its simplicity and robustness, particularly because it avoids recursion stack issues. While DFS-based topological sorting is another viable option, it requires additional post-processing to calculate the longest path, which adds unnecessary complexity. In conclusion, the BFS-based topological sorting method strikes the best balance between efficiency, simplicity, and scalability, making it the most suitable choice for solving this problem. To determine the minimum number of semesters required to complete all courses, we use a topological sorting approach, which is particularly well-suited for problems involving directed acyclic graphs, or DAGs. Here, each course is represented as a node, and prerequisites are represented as directed edges connecting these nodes. The first step involves input parsing. We represent the courses and their prerequisites using an adjacency list, which is an efficient structure for storing relationships in a graph. Alongside this, we maintain an indegree array, which keeps track of the number of prerequisites for each course. For example, if course 3 has 2 prerequisites, its indegree value will be 2. The next step is graph construction. As we process each prerequisite pair, we populate the adjacency list by adding the dependent course to the list of its prerequisite. Simultaneously, we update the indegree array, incrementing the indegree of the dependent course by 1 to reflect this new dependency. This step sets up the foundation for the algorithm by organizing the courses and their relationships in a structured way. Once the graph is constructed, we move to the initialization phase of the topological sorting process. Here, we use a queue to store courses with an indegree of 0, meaning courses that have no prerequisites and are ready to be taken immediately. We also initialize a counter called semesters to 0, which will track the number of semesters required to complete all courses. The core of the algorithm lies in the BFS, or breadth-first search, traversal for topological sorting. While the queue is not empty, we increment the semesters counter at the start of each iteration, indicating the start of a new semester. During this semester, all courses currently in the queue can be taken in parallel. For each course, we remove it from the queue and process its neighbors in the adjacency list. This involves decrementing the in-degree of each neighbor, as one of their prerequisites has now been satisfied. If any neighbor's in-degree becomes 0, it is added to the queue, indicating that it is now ready to be taken in the next semester. This step-by-step processing ensures that courses are completed in the correct order. After processing all courses, we perform a final check to ensure that all in-degrees are 0. If any course still has a non-zero in-degree, it means there is a cycle in the graph, which makes it impossible to complete all courses. This mechanism ensures correctness and detects unsolvable cases. Finally, we return the result. If the graph is valid, the semesters counter provides the minimum number of semesters required to complete all courses. This result reflects the structure of the graph and the dependency levels within it. A few key insights emerge from this approach. First, topological sorting is central to ensuring that courses are taken in the correct order, respecting all prerequisite relationships. By processing the graph level by level, we ensure that dependencies are handled systematically. Second, the use of BFS allows us to process courses in parallel within each level, which corresponds to a semester. This makes the approach both efficient and intuitive. Lastly, cycle detection is a critical aspect of the algorithm. If a course remains unprocessed, meaning its in-degree is still non-zero at the end, it indicates a prerequisite loop. In such cases, the algorithm identifies the graph as invalid, making it clear that completing all courses is impossible. These insights highlight the power of combining graph theory with BFS for solving scheduling problems. To implement this algorithm effectively, we rely on three key data structures. The adjacency list is used to represent the graph, allowing efficient access to the neighbors of each course. The queue is essential for facilitating the BFS process, ensuring that courses are processed in the correct order based on their prerequisites. The in-degree array helps us track the remaining prerequisites for each course, enabling quick identification of courses that are ready to be taken. It's also important to consider edge cases. For instance, if the graph is disconnected, meaning some courses have no dependencies and are not prerequisites for others, these courses will naturally be processed independently. If there's a cycle in the graph, such as a prerequisite loop, the algorithm will detect it and correctly conclude that the courses cannot be completed. In cases where no courses have prerequisites, all courses can be taken in parallel, resulting in just one semester. On the other hand, if the graph forms a single chain of dependencies, each course will require its own semester, equal to the total number of courses. These considerations ensure that the algorithm handles all scenarios robustly. Now, let's analyze the complexity of the algorithm. The time complexity is determined by two main steps: graph construction and BFS traversal. Constructing the graph involves iterating through all edges, which takes O(e), where e is the number of prerequisites. The BFS traversal takes O(n plus e), where n is the number of courses and e is the number of edges. Combining these, the overall time complexity is O(n plus e). For space complexity, the adjacency list requires O(n plus e) to store the graph, as it includes all nodes and edges. The queue and in-degree array each require O(n) space, as they are proportional to the number of courses. Adding these together, the total space complexity is also O(n plus e). This efficient use of time and space ensures that the algorithm scales well even for large problem instances, making it a practical solution for determining the minimum semesters required to complete a set of courses. To solve the problem of determining the minimum number of semesters required to complete all courses, we start by setting up the necessary data structures. We import Deque to efficiently manage our queue and default Deque to build our adjacency list for the course graph. Within the minimum semesters method, we first initialize the graph as a default Deque of lists and create an in_degree array to track the number of prerequisites for each course. The length of this array is n plus 1 to account for the one-based indexing of courses. Next, we iterate over the relations input, which contains pairs of prerequisites and courses. For each pair, we add the course to the adjacency list of its prerequisite and increment its in-degree by 1. After constructing the graph and in-degree array, we prepare for the topological sort by initializing a queue. This queue will hold all courses that have no prerequisites, which we determine by iterating through the in_degree array. Any course with an in-degree of 0 is added to the queue. Now, we introduce two variables, semester to keep track of the number of semesters and completed_courses to count how many courses we have successfully processed. We then enter a while loop to perform the topological sort as long as there are courses in the queue. Within the while loop, each iteration represents one semester, so we increment the semester counter at the start of each iteration. For every course currently in the queue, we process it by dequeuing it and incrementing the completed_courses counter. Then, for each course dependent on the current course, which we find in the adjacency list, we decrement its indegree. If the indegree of a dependent course becomes 0, we add it to the queue since it is now ready to be taken. Once the queue is empty, meaning all possible courses have been processed, we check if the number of completed_courses matches n, the total number of courses. If they are equal, it means we successfully completed all courses and return the semester count. However, if completed_courses is less than n, it indicates the presence of a cycle in the graph, making it impossible to complete all courses. In this case, we return -1 as the result. To implement the solution in Java, we start by importing the necessary utility classes. The function minimum semesters takes two inputs, the total number of courses n and a 2D array relations that defines the prerequisite relationships between courses. First, we build an adjacency list to represent the course dependencies and an integree array to count the number of prerequisites for each course. For every pair in relations, we extract the prerequisite and the dependent course, adding the dependent course to the adjacency list of the prerequisite. Simultaneously, we increment the integree of the dependent course to track its prerequisites. Next, we initialize a queue to store courses that have no prerequisites. By iterating through all courses, we add any course with an integree of 0 to the queue, as these are the courses that can be taken immediately. We also prepare variables for tracking the number of semesters and the count of completed courses, setting both to 0 initially. Finally, we begin the topological sort using a while loop. The while loop processes the courses in the queue level by level, where each level represents a semester. At the start of each iteration, we determine the size of the queue, representing the number of courses we can complete in the current semester. We increment the semester counter and then process each course in the queue. For every course, we remove it from the queue and increment the count of completed courses. If the course has dependent courses in the adjacency list, we decrease their integree by 1. If a dependent course's integree becomes 0, it means all its prerequisites are completed, so we add it to the queue. This process continues until the queue is empty. After the loop, we check if all courses have been completed by comparing completed courses to n. If they match, we return the number of semesters. Otherwise, if some courses remain incomplete, it indicates the presence of a cycle in the graph, so we return -1. Here, we start with a simple case where there are no cycles in the course dependencies. The input specifies that we have 3 courses in 2 relations. Course 1 must be completed before Course 3, and Course 2 must also be completed before Course 3. To solve this, we first build the graph and the integree array. The graph represents the dependencies, so for relation 1, 3, we add 3 to the list of neighbors for Course 1 in the graph, and for relation 2, 3, we do the same for Course 2. At the same time, for each dependency, we increment the integree of the dependent course. After processing both relations, our graph shows that Course 3 depends on Courses 1 and 2, while the integree array reflects that Course 3 has 2 prerequisites. Next, we initialize the queue with courses that have no prerequisites, which means their integree is 0. In this case, Courses 1 and 2 have no dependencies, so they are added to the queue. We also initialize variables to track the number of semesters and the count of completed courses. Now, we process the courses in the queue using topological sorting. In the first semester, we increment the semester count to 1 and process the courses in the queue, which are Courses 1 and 2. First, we remove Course 1 from the queue and reduce the integree of its dependent, Course 3, by 1. Then, we do the same for Course 2, and this time the integree of Course 3 becomes 0, so we add it to the queue for the next semester. At the end of the first semester, the queue contains only Course 3, and we have completed 2 out of the 3 courses. In the second semester, we increment the semester count to 2 and process Course 3, marking it as completed. With the queue now empty and all 3 courses completed, we confirm that the process is finished. Since all courses have been completed in 2 semesters, we return 2 as the output. Here, we examine a more complex case that involves a cycle in the course dependencies. The input specifies 4 courses in several relations. Course 1 depends on Course 2, Course 2 depends on Course 3, Course 3 depends on both Courses 1 and 4. When we build the graph and in-degree array, we see that Course 3 has 2 outgoing edges, one to Course 1 and another to Course 4. The in-degree array is updated accordingly, showing that all courses have at least one prerequisite. However, when we initialize the queue, we find that no course has an in-degree of 0, meaning there are no courses that can be taken without prerequisites. This indicates a problem. Since the queue remains empty and the number of completed courses is still 0, it's clear that the graph contains a cycle, making it impossible to complete all courses. In such cases, we return -1 to indicate that the task is not feasible. In this example, we look at a scenario where all courses are independent, meaning there are no dependencies between any of them. The input specifies 4 courses and no relations. When we construct the graph and in-degree array, the graph remains empty, and the in-degree array shows that all courses have an in-degree of 0. This means all courses can be taken immediately, so we add all 4 courses to the queue. In the first semester, we process all courses in the queue, marking them as completed. Since there are no dependencies, the queue becomes empty after processing all the courses, and the number of completed courses matches the total number of courses. As all courses are completed in just 1 semester, we return 1 as the output. When analyzing the time complexity of this problem, we break it down into 3 main steps. First, constructing the graph and the in-degree array requires iterating through the list of relations, which takes m time, where m is the number of prerequisite relations. Next, during queue initialization, we check each course from 1 to n to identify those with 0 prerequisites, which takes n time. Finally, the topological sort processes each course exactly once, adding and removing it from the queue only when its in-degree becomes 0. For each course, we traverse its outgoing edges, which collectively amount to m edges being processed during the traversal. This step has a time complexity of n plus m, as we handle both the nodes and edges in the graph. Altogether, these 3 steps form the foundation of the algorithm's time complexity. To determine the total time complexity, we simply combine the individual components. The graph construction step takes m, queue initialization takes n, and the topological sort operates in n plus m. When we sum these, the overall time complexity becomes n plus m. Here, n represents the number of courses, and m represents the number of prerequisite relations. This linear relationship between the nodes and edges ensures the algorithm remains efficient even for larger inputs, making it feasible for real-world scenarios involving dependency management. Now let's turn to the space complexity. The algorithm's space requirements are driven by the graph representation, the in-degree array, and the queue. First, the adjacency list graph is used to store outgoing edges, which requires m space since it contains all m edges. Second, the in-degree array, which has n plus 1 entries to accommodate 1-based indexing, requires n space. Lastly, the queue, which holds courses with 0 prerequisites, can hold up to n courses at once in the worst case, contributing an additional n space. These components together define the space complexity of the algorithm. Adding up the space requirements gives us the total space complexity of n plus m. The graph requires m, while the in-degree array and queue each require n. This means the space complexity grows linearly with the input size, depending on the number of courses and prerequisite relations. Looking at different cases, in the best case where there are no prerequisites, the graph has no edges, and the algorithm only processes the n courses with a time and space complexity of n. In the average case, both n and m contribute to the complexity, resulting in the typical n plus m. In the worst case, where every course depends on another, the algorithm must handle all n courses and all m edges, but the complexity remains n plus m, for both time and space. This predictable behavior is one of the strengths of the algorithm. When comparing this approach to a naive solution, we see a dramatic improvement in efficiency. A brute force method would involve recursively generating all permutations of the n courses to find a valid order, resulting in a factorial time complexity of n. This is computationally infeasible for large n. In contrast, the topological sort approach leverages the structure of the directed acyclic graph to systematically resolve dependencies, achieving a far more efficient O(n+m) complexity. This efficiency stems from processing each node and edge exactly once. Mathematically, constructing the graph an in-degree array is linear in the number of edges, taking O(m). The topological sort then processes all nodes and edges in O(n+m). This linear scaling ensures the algorithm performs well even on large graphs, making it a practical solution for problems involving dependency resolution. One of the most common mistakes in solving the parallel courses problem is confusing topological order with a simple breadth-first search traversal. It's important to remember that topological sorting ensures nodes are processed only after all their prerequisites are completed. This distinction is critical because failing to honor the dependency order can lead to incorrect results. To avoid this, you can use Kahn's algorithm, which systematically processes nodes with 0 in degree, or a depth-first search approach combined with a stack to capture the correct order. Another frequent error is mishandling cycles in the graph. If there's a cycle in the prerequisites, it means the courses cannot be completed, yet some solutions fail to detect this, resulting in infinite loops or incorrect answers. To address this, you can use a visited set during DFS or maintain an in-degree table to identify cycles. Lastly, disconnected graphs are another pitfall. If the graph contains multiple disconnected components, some solutions only handle one connected component and miss others. This can happen when nodes with 0 in degree are ignored. The fix here is to ensure that your algorithm processes all nodes, including those with no prerequisites, so that every course is accounted for. Another area to watch out for is inefficiency when handling large inputs. If your solution repeatedly rebuilds the in-degree array or uses redundant nested loops, it can become computationally expensive, especially when working with constraints like n equals 10 to the power of 4. To optimize, you should use adjacency lists to store graph relationships and update in-degree values only when necessary. This minimizes unnecessary recalculations. Additionally, misinterpreting the problem statement is a common source of errors. For example, some solutions fail to meet the requirement of completing courses in the minimum number of semesters. Instead of prioritizing layer-by-layer processing, they might process nodes in an arbitrary order, leading to suboptimal results. To get this right, you need to group courses by semester, which can be achieved by processing the graph in levels using a level-order traversal approach. This ensures that courses are completed as early as possible while respecting the prerequisites. When preparing for interviews, it's helpful to recognize that the parallel courses problem is essentially a variation of the topological sorting technique. Strong knowledge of graph traversal methods, such as depth-first search, breadth-first search, and Kahn's algorithm, is crucial. It's also important to focus on time complexity, aiming for solutions with O of v plus e, and to optimize space usage, as brute force solutions are impractical for large-scale inputs. During discussions, you should highlight edge cases like graphs with cycles, which indicate that the courses cannot be completed, and graphs with multiple disconnected components, where all components must still be processed. Additionally, consider edge cases such as graphs where no courses have prerequisites, meaning all courses can be taken independently, or scenarios with a single course that has a large number of prerequisites. Addressing these cases demonstrates a comprehensive understanding of the problem and its nuances. This problem is closely related to several other graph-based challenges that are worth reviewing. For instance, in the course schedule problem, LeetCode number 207, the goal is to determine if it's possible to complete all courses given their prerequisites, which essentially involves validating a topological sort. Similarly, course schedule 2, LeetCode number 210, asks you to find a valid order to complete courses, which requires outputting a topological sort. Another related problem is minimum height trees, LeetCode number 310, where you reduce the graph iteratively to find tree centers, using BFS or DFS techniques. Finally, sequence reconstruction, LeetCode number 444, involves verifying if a sequence can be uniquely reconstructed using a topological order. Exploring these problems can deepen your understanding of graph traversal and help you recognize patterns applicable to parallel courses. There are several alternative approaches to solving the parallel courses problem, and each comes with its own strengths and trade-offs. A DFS-based topological sort involves performing a depth-first search and grouping nodes by the depth of their recursive stack calls. While effective, this approach can require extra memory for the recursion stack, and cycle detection can be more challenging to implement. Alternatively, Kahn's algorithm uses a BFS approach, where nodes with 0 in degree are processed in queue order, and semesters are counted as levels of BFS. This method simplifies cycle detection and works particularly well for sparse graphs. Another less common approach involves dynamic programming to calculate the longest path in the graph, where the path length corresponds to the number of semesters. While this method is conceptually interesting, it's often slower and less intuitive than BFS or DFS, making it less practical for competitive programming or large inputs. Understanding these alternatives allows you to choose the most appropriate method for different scenarios. Great work! To wrap up, we reviewed how to tackle the parallel courses problem with a graph-based approach. Topological sorting, using BFS or Kahn's algorithm, was key to solving this. Remember, this technique is invaluable for dependency resolution problems. Thanks for tuning in, see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!